Welcome to DAR Tutors for online and home tuition. Hello and welcome. Today, we will be covering key concepts from IB Mathematics, Applications and Interpretation Higher Level, specifically, Chapter 10, Points in Space. In this video, we will build a solid foundation in three-dimensional coordinate geometry. This is a crucial topic for understanding the world around us and is a common feature in the IB curriculum. By the end of this session, you will be able to perform three main tasks. First, specify points and calculate distances and midpoints in 3D. Second, find the surface area and volume of 3D solids. And third, use trigonometry to find angles in 3 dimensions. Let's begin. We'll start with the fundamental concept of three-dimensional coordinate geometry. To describe the location of any point in space, we need a system. Imagine extending the 2D coordinate plane we're familiar with. We do this by adding a third axis, which we call the z-axis. This axis is perpendicular to both the x and y axes at the origin. Now, any point in space can be uniquely identified by its position along each of these three axes. We represent this with an ordered triple. This ordered triple is in the form x, y, z, z. It tells us how far to move from the origin in the x, y, and z directions, respectively. Let's visualize this. Suppose we want to plot the point 3, 4, 2. We start at the origin, 0, 0, 0. First, we move 3 units along the positive x-axis. From there, we move 4 units in the positive y direction, parallel to the y-axis. And finally, we move 2 units in the positive z direction, straight up. This process allows us to pinpoint any location in our three-dimensional world using a simple set of numbers. It's a powerful tool that transforms geometry into algebra. Now that we can identify points, our next objective is to find the distance between them. We can derive a formula for this using the Pythagorean theorem, which we are familiar with from 2D geometry. Consider a rectangular prism. Let the length, width, and height be A, B, and C. First, let's find the length of the diagonal AC on the base. Using the Pythagorean theorem, AC squared equals a squared plus B squared. Next, consider the diagonal AB that goes from the bottom front to the top back. Triangle ACB is a right-angled triangle, so AB squared equals AC squared plus C squared. Now, we can substitute our first result into the second one. AB squared becomes a squared plus B squared plus C squared. Therefore, the distance AB is the square root of a squared plus B squared plus C squared. This is the core idea. Let's formalize it. Suppose we have 2 points A and B. Let A be x1, y1, z1, and B be x2, y2, z2. The distance formula is AB equals the square root of the quantity x2 minus x1 squared plus the quantity y2 minus y1 squared plus the quantity z2 minus z1 squared. This is a direct extension of the 2D distance formula. It measures the straight line distance, often called the Euclidean distance, between any 2 points in 3D space. It's a fundamental tool for solving many problems in this chapter. Just as with distance, the midpoint formula also extends naturally into 3 dimensions. The midpoint of a line segment is the point that divides the segment into 2 equal parts. In 3D, this point has its own x, y, and z coordinates. If our 2 points are A at x1, y1, z1, and B at x2, y2, z2, the coordinates of their midpoint, m, are found by averaging the corresponding coordinates. So the x-coordinate of the midpoint is x1 plus x2 divided by 2. The y-coordinate is y1 plus y2 divided by 2. And the z-coordinate is z1 plus z2 divided by 2. This formula provides the exact coordinates of the point that lies precisely halfway along the line segment connecting A and B. We will now apply these formulas to a worked example. Let's work through an example to see these formulas in action. Consider 2 points, coordinates 4, 3, 1, and B with coordinates 2, 4, 1. Our goal is to find the distance between them, AB, and the coordinates of the midpoint of the segment AB. To make our calculation clear, let's identify the coordinates for A as x1, y1, z1, and for B as x2, y2, z2. First, let's find the distance AB using our distance formula. We substitute the values into the formula. The square root of 2 minus 4 squared plus 4 minus 3 squared plus 1 minus 1 squared. Simplifying the expressions inside the parentheses, we get the square root of 6 squared plus 7 squared plus 2 squared. Now we square each term, 36 plus 49 plus 4. Adding these together gives us the square root of 89. Since 89 is a prime number, this is our exact answer. The distance AB is root 89 units. Next, let's find the midpoint of AB using the midpoint formula. We average the x-coordinates, 4 plus 2, over 2. We average the y-coordinates, 3 plus 4, over 2. And we average the z-coordinates, 1 plus 1 over 2. This simplifies to 2 over 2, 1 over 2, 0 over 2, which gives us the coordinates 1/2, 0. So the midpoint of the segment AB is 1/2 of 0. We have now successfully applied both the distance and midpoint formulas in 3 dimensions, which meets our first learning objective. Our second objective involves calculating the surface area and volume of 3D solids. We can use our knowledge of 3D coordinates to define these solids and then apply standard measurement formulas. We will focus on a specific solid, the square-based pyramid. Let's consider a pyramid defined by its base coordinates and apex. Imagine a base in the xy plane and an apex on the z-axis. A square-based pyramid has a base with vertices O, 0, 0, 0, A4, 0, 0, B4, 4, 0, and 4, 0. The apex, or top point, is at D225. A common first step in these problems is to verify that the apex is directly above the center of the base. This simplifies our calculations significantly. For a square, the center is the midpoint of its diagonals. Let's find the midpoint of the diagonal OB. The midpoint is 0 plus 4, 2, 0 plus 4, 2, 0 plus 2, which simplifies to 2, 2, 0. Notice the coordinates. The x and y coordinates of the center of the base are 2, 2, and the z coordinate is 0, since the base lies in the xy plane. Comparing this to the apex, D2002-5, we see that the x and y coordinates are identical. The only difference is in the z coordinate. This confirms that the apex D lies directly above the center of the base. Now, let's proceed with finding the volume of the pyramid. The formula for the volume of any pyramid is 1/3 times the area of its base times its perpendicular height. We need to find 2 things, the area of the base and the height. The base is a square with vertices O, 0, 0, A4, 4, 4, and C0, 4. The length of each side is 4 units. The area of the base is simply side length times side length, which is 4 times 4, or 16 square units. Next, the height. The height of the pyramid is the perpendicular distance from the apex to the plane of the base. We found the center of the base to be 2002, and the apex D is at 2002.5. The height is the difference in their z coordinates. This is 5 minus 0, so the height is 5 units. Now we can calculate the volume. Plugging in our values, the volume is 1/3 times 16 times 5, which equals 80 over 3 cubic units. For the IB exam, it's often best to leave answers as exact fractions unless specified otherwise. Finally, for our pyramid, let's find the surface area. The total surface area of this pyramid is the sum of the area of its square base and the area of its 4 triangular faces. We already know the base area is 16, so we just need to find the area of one triangular face and multiply by 4. The triangular faces are isosceles. To find their area, we need their base and perpendicular height. Let's consider the face on side BC. The coordinates are B4 4,000 and C4 4,000. The length of the base BC is the difference in x-coordinates, which is 4 units. The midpoint M of the base BC is found by averaging the coordinates 4 plus 0, 2, 4, 4, 2, 0 plus 0, 2, giving us 2, 4, 0. The perpendicular height of this triangular face is the distance from the apex D225 to the midpoint M2 4,000. This is called the slant height. Let's calculate this distance, MD. Using the distance formula, we get the square root of 2 minus 2 squared plus 4 minus 2 squared plus 0 minus 5 squared. This simplifies to the square root of 0 plus 4 plus 25, which is root 29 units. Now we can find the area of one face. The area of a triangle is 1/2 times its base times its height. This is 1/2 times 4 times root 29, which equals 2 root 29 square units. Since the pyramid has 4 identical faces, the total surface area is the base area plus 4 times the face area. So the total surface area is 16 plus 4 times 2 root 29, which gives us an exact answer of 16 plus 8 root 29 square units. This value is approximately 59.1, rounded to 3 significant figures. By calculating both volume and surface area, we have now achieved our second learning objective for measurement. We have now reached the 10-minute mark. If you are enjoying this lesson and would like to explore these concepts in more detail with personalized support, I invite you to contact DAR Tutors. Our team provides expert tuition in IB, A-Level, and IGCSE curricula, both online and at home. We can help you build your confidence and achieve your academic goals. Thank you for considering DAR Tutors for your learning journey. Now, let's continue with our lesson on points in space. Our third and final learning objective is to apply trigonometry to find angles in three-dimensional figures. The key here is to identify and isolate right-angled triangles hidden within the 3D shape. Let's find the angle between the line segment EC and the base plane ABCO of this cuboid. The base plane is the floor of the cuboid. The line segment EC starts from the top back corner and goes to the bottom front corner. To find the angle a line makes with a plane, we project the line onto the plane. The projection of EC onto the base is the diagonal AC. The angle we are looking for is the angle between the line EC and its projection AC. This forms a right-angled triangle, ECA, with the right angle at A. To use trigonometry in this triangle, we need the lengths of at least 2 of its sides. First, side AE. A is at 5,000 and E is at 5,003. AE is a vertical line. Its length is the difference in z-coordinates, which is 3 units. Next, side AC. This is a diagonal on the base plane. We'll use the distance formula in 2D. AC squared is 5 squared plus 4 squared, which is 25 plus 16, or 41. Now we have 2 sides of the right-angled triangle ECA. Let's label the angle we want to find, angle ACE as theta phi. From the perspective of angle theta, side AE is the opposite side, and side AC is the adjacent side. The trigonometric ratio that relates opposite and adjacent is tangent. So, tan theta equals opposite over adjacent, which is AE over AC. Substituting the lengths, we get tan theta equals 3 over the square root of 41. To find theta, we take the inverse tangent. Theta is the inverse tan of 3 over root 41, which is approximately 25.1 degrees. So the line segment EC makes an angle of about 25.1 degrees with the base plane. We have successfully applied trigonometry to a 3D figure. Trigonometry isn't just for right-angled triangles. We can also find angles within a triangle in 3D that is not right-angled, using the cosine rule. The cosine rule allows us to find an angle of a triangle if we know the lengths of all 3 sides. Let's work through an example. We are given 3 points, P1, 4, 5, Q2, 0, 1, and R0, 2, 6. We want to find the angle PQR, which is the angle at vertex Q. First, we must find the lengths of the 3 sides of triangle PQR. Using the 3D distance formula, we find the length of side PQ. This calculates to the square root of 41 units. Next, we find the length of side PR. Substituting the coordinates of P and R, we get the square root of 38 units. Finally, we find the length of side QR. Plugging in the coordinates of Q and R, we get the square root of 33 units. Now we have all 3 side lengths. We can apply the cosine rule. The cosine rule states that c squared equals a squared plus b squared minus 2ab QoS To find angle Q, we'll rearrange the formula to QoS Q equals PQ squared plus QR squared minus PR squared, all over 2 times PQ times QR. Substituting our values, cos Q equals 41 plus 33 minus 30, all over 2 times root 41 times root 33. This simplifies to 18 over the square root of 1353. Taking the inverse cosine, we find that the angle Q is approximately 60.7 degrees. So angle PQR is about 60.7 degrees. We have now covered the 3 main areas for this topic: points in space, measurement, and trigonometry. To reinforce these concepts and help you prepare for your IB exams, We will now work through 5 IB-style practice questions. I encourage you to pause the video after each question appears and try to solve it on your own before watching the solution. This is an excellent way to consolidate your understanding. Here is our first question. Take a moment to read the question and formulate your strategy. Pause the video if you want to solve it yourself. Okay, let's look at the solution. The first step is to find the midpoint of BC. Let's call it M. Using the midpoint formula for B and C, we get 4 plus 2, 2, 5 plus 3, 2, 2 plus 0, 2, which simplifies to 1, 1, 1. So the midpoint M is at 1, 1, 1. Now we need to find the distance between A, 6, 1 plus 4, and this new point 1, 1, 1. We use the distance formula. The distance AM is the square root of 1 to 6 squared plus 1 to 1 squared plus 1, 4 squared, which simplifies to the square root of 50. This is our final answer. The distance is root 50 units. We can also simplify this to 5 times the square root of 2. This question combines both the midpoint and distance formulas, showing how they often work together. Here's our second practice question. Again, pause the video to work through this problem on your own. Let's review the solution. We need to find the height of the cylinder given its volume and information about its base. First, we need to find the radius of the base. The base is centered at the origin, 0, 0, and a point on its edge is 3 to 4 thalers. The radius, r, is the distance from the center to this point. Using the distance formula, the radius is the square root of 3 squared plus 4 squared, which is the square root of 25. So the radius is 5 units. Yes. Now we have the radius. The problem also gives us the volume. The volume of a cylinder is P times R squared times H. We are told the volume is 150 pi, and we just found that the radius R is 5. We can plug these values into the formula. This gives us 150 pi equals 25 pi times H. We can divide both sides by 25 pi to isolate H. 150 pi divided by 25 pi is 6. Therefore, the height of the cylinder is 6 units. Question 3 asks us to determine the nature of a triangle. Recall that a scalene triangle has no equal sides. An isosceles triangle has 2 equal sides, and an equilateral triangle has 3 equal sides. Pause to work it out. The strategy is to find the length of each side and then compare them. First, for side AB, the distance formula gives us the square root of 1 squared plus 3 squared plus 0 squared, which is the square root of 10. Next, for side BC, the distance formula yields the square root of 3 squared plus 4 squared plus 3 squared, which is the square root of 34. Finally, for side AC, we find the square root of 4 squared plus 1 squared plus 3 squared, which is also the square root of 26. Now we compare the lengths, root 10, root 34, and root 26. Since all 3 lengths are different, the triangle ABC is scalene. A quick check. Could it be a right-angled triangle? If it were, the Pythagorean theorem would hold. Root 10 squared plus root 26 squared equals to 10 plus 26 equals 36. Root 34 squared equals 34. Since 36 is not equal to 34, it is not a right-angled triangle. It is purely scalene. Our fourth question is another trigonometry problem, but this time asking for an angle between 2 lines, not a line and a plane. The angle BAC is the angle at vertex A. This means the angle is formed by the line segments AB and AC. Since this triangle is unlikely to be right-angled, we'll use the cosine rule. Pause and try it. To find the angle at A, we need the lengths of all 3 sides, AB, AC, and BC. The length of AB is the square root of 5 squared plus 1 squared plus negative 1 squared, which is the square root of 27. The length of AC is the square root of negative 1 squared plus 2 squared plus negative 2 squared, which is the square root of 9, or simply 3. The length of BC is the square root of negative 6 squared plus 1 squared plus negative 1 squared, which is the square root of 38. Now we can apply the cosine rule for angle A. The cosine of angle A equals AB squared plus AC squared minus BC squared, divided by 2 times AB times AC. Plugging in our values, 27 plus 9 minus 38 over 2 times root, 27 times 3. This simplifies to negative 2 over 6 times the square root of 27. Calculating this gives approximately negative 0.0641. The angle A is the inverse cosine of this value, which is approximately 93.7 degrees. The negative cosine indicates it's an obtuse angle. Our final question is a more complex pyramid problem requiring multiple steps. Question 5. A square-based pyramid has base O000, 800, B80, 080. The apex is D4.46. M is the midpoint of AB. Find the measure of angle MD. Pause and think about how to tackle this. It combines several ideas we've covered. To find angle MDB, which is at vertex D, we need the side lengths of triangle MDB. The three sides are DM, MB, and DB. Let's find them one by one. First, we need the coordinates of M, the midpoint of AB. A is at 8,0, and B is at 8,0. The midpoint M is 8 plus 8, 2. 0 plus 8, 2. 0 plus 0, 2, which is 840. Now we have all the coordinates needed for our triangle. Let's find the side lengths. Side MB. M is 840 and B is 888. MB is a horizontal segment. Its length is the difference in y coordinates, which is 4 units. Side DM. D is 446 and M is 84000. The distance DM is the square root of 4 squared plus 0 squared plus 6 squared, which is the square root of 52. Side DB. D is 446 and B is 888. The distance dB is the square root of 4 squared plus per 6 squared, which is the square root of 68. We now have all three side lengths. We can use the cosine rule to find the angle. Cos MDB, dm squared plus db squared minus mb squared, divided by 2 times dm times db. This is 52 plus 68 minus 16 over 2 times root 52 times root 68. This simplifies to 52 over the square root of 3536. The inverse cosine of this value gives us an angle of approximately 29.5 degrees. So, angle MDB is approximately 29.5 degrees. Let's quickly recap what we've accomplished in this session. We began by defining the 3D Cartesian coordinate system using x, y, and z axes. We then derived and applied the distance and midpoint formulas for points in space. Next, we used these tools to calculate the volume and surface area of complex 3D solids, specifically a square-based pyramid. And finally, we applied trigonometry, including the cosine rule, to find various angles within 3D figures. We also worked through 5 IB-style practice questions to solidify your understanding. These are the core skills you'll need for this topic in your IB Applications and Interpretation higher-level course. I hope this video has been helpful. Keep practicing these concepts, and you will build a strong foundation for future topics. Thank you for watching. This lesson was brought to you by DAR Tutors. For more expert tuition and personalized learning experiences in IB A-Level and IGCSE mathematics, please visit us online or contact us directly. Thank you.